the reason why I have this talk is I've seen people using BLE usually like through these modules, and you essentially are completely hidden from the protocol, but that results, for example, that people are often not very aware about, for example, the privacy implications of Bluetooth Low Energy, or, for example, the security vulnerabilities related to Bluetooth Low Energy. So usually if I try to understand the security of a system, I build hardware, and I will show you some like projects from my past where I built like similar projects because of curiosity about the security aspect of the technology. And I did a similar thing again for Bluetooth Low Energy. And that's essentially the content of my talk. So essentially, I love breaking things. I live in Cambridge. I work for ARM on Internet of Things. Surprise, surprise. I'm mostly responsible for security aspects. So for example, I essentially want to establish basically the same security concepts that were basically enabled by Unix and other systems like 20, 30 years ago or more. And essentially what I realized that people are doing the same silly mistakes again with embedded computing. And essentially you again have like a single process space, everything has access to everything, which is like plain out silly. And I'm doing something about that and write some software for existing Cortex M3, M4 type microcontrollers to have basically these advanced security models, and will facilitate basically future security extension in ARM CPUs using the same software. So essentially that's my background. I will talk about the other open source and open hardware projects later a bit. Yeah, and essentially when it's low power, I like it. That's essentially the thing. And when I'm bored, I'm playing with RGB strips. That's one of the things here. Currently it's set to FFT mode and just RGB LEDs, but I do light painting with that as well. So that's basically, I think, the first security-related project I created. I think back then, in the days, 2005, it was. Passive RFID was the big thing, like for ticketing and so on. And you couldn't do sensible security research because you only could get proprietary readers where you only had, again, like very high-level access to these protocols. And people made silly design decisions about, oh yeah, I can't clone these cards because I can't get a card because I can't get a card with the same ID, but surprise, surprise, if I can emulate the card, then suddenly I can pretend to be everyone and just copy cards and so on. And that's one of the reasons. Like that's actually the version 2 of this OpenPCD project, which supports already NFC. But there was a very early version, OpenPCD 1, that was, for example, used in breaking Mifare Classic. So like the Oyster cards used in London were broken partly because of my hardware. I'm pretty proud of that. Yeah. And the idea is to basically have as few as possible layers that obstruct, for example, your timings, give as much as possible access to that. And for example, if these chips have debug signals, you want to have access to that because you want to use your scope, for example, for figuring out, does my, for example, RFID emulator break the RFID protocol or not without having super expensive bench scopes. So basically, it's kind of a facilitator for that. And right after that, essentially, I realized, yeah, actually this passive RFID stuff is super boring. So in 2006, I decided, yeah, let's build something where we can play with security nightmares that we have in 10 years, which is next year. So that's essentially the 10 years. And essentially, the idea was to predict, okay, how will people use this RFID technology once it's grown up? And my prediction turned out to be pretty accurate. So in 2006, we did RFID tracking of people in buildings. So essentially, there was a large conference with 1,000 attendees. We handed out these tags, and we were tracking people in real time. And did do data mining, but already back then we had protocols which are still way beyond what you get currently for iBeacon and crap like that, where you don't have any privacy. Basically, everyone can spoof these tags. That stuff already in 2006 was fully encrypted and protected against replay attacks and stuff like that. So I'm a bit smug about that. And Apple stole my name with iBeacon. So yeah, and there were some spin-off projects from this OpenBeacon project. One of them I'm particularly proud of. We created basically an art project which was used in Toronto for yeah, building installation was a temporary thing in Louis Blanche. We built 960 dimmers that received pixel data via 2.4 gigahertz in real time. We had these, we created also these wireless gateways that receive UDP packets with basically image data via Ethernet, retransmit that with wireless in real time. So frame rate was like 20 something hertz. And the result was basically the Toronto City Hall, where we put essentially, so we only build the hardware, but others basically then wrote a very nice software for that, where people could upload movies, and essentially we basically played back videos on like all these 4 areas of the Toronto City Hall. And yeah, so this is how you do proper Internet of Things lighting. Yeah, and some minor project which I used to get over boredom, which is this RGB strip. So you see some pictures of that. When you download the PDFs, you can click on the images to see the thing. And I'm recently started loving 3D printing, so that is a high power Nerf gun with CO2 capsules, which was fun to design. For this Bluetooth Low Energy security research, created a new tag. So essentially, like we, in that sense, is me and my wife. So we had essentially like a 2-person company in Berlin. Now we moved to Cambridge. And she usually is doing the hardware design, and I'm doing the software and like the conceptual designs. And this latest OpenBeacon tag we were using already for quite a while for like customer projects, but we decided to release the design under open hardware license, which we did like half a year ago or something, and released again like the hardware design files. The firmware anyway is available for download, and I will use that for security research, and I created some interesting firmware already, which is a good start for future research. So let me give you a quick overview of Bluetooth Low Energy, just basically like a quick crash course. It's in the same frequency range as Wi-Fi. You have 40 channels, which are 2 megahertz spaced. And if you use proper antennas, you can easily reach 150 meters with Bluetooth Low Energy, which is pretty exciting. And because it's 1 megabit, also it's pretty good in penetrating walls and stuff. And you can set the system up in a connectionless mode, which removes a lot of trouble you normally get under like in this 2-way communication links, which proved to be extremely robust for tracking. So think of a tracking situation. You have like 900 people wearing these badges in the same room. And you can imagine that like with a normal bidirectional protocol, you can't win that situation because like you would have retransmits because, yeah, don't have to explain further. So, but if you have like this protocols that don't expect immediate answers and Bluetooth Low Energy is perfect for that, then suddenly you have a super scalable system where you easily can handle thousands of tags with a packet rate. Like when I talk about 900 people, then I talk about a packet rate of at least 8 packets per second from each tag that we needed for high resolution locationing. So you get around 8,000 packets per second per reader. So usually I had like 20, 30 readers. You can do the math. It's quite a brutal packet rate you get on your server from something unsuspicious like Bluetooth. So the interesting part on Bluetooth Low Energy, so most of the stuff you see is currently very simple and boring, including ours. It's essentially just the so-called advertisement mode. So the tag sits there, just says, hey, yeah, I'm here, and this is my transmit power, and let me do some locationing for you. And usually the locationing thing is done in an app. And for this purpose, there are 3 advertisement channels. So these 3 advertisement channels are essentially the beginning, the middle, and the end of the Wi-Fi band. And the reason is that if you have like troublesome Wi-Fi environment, or some, for example, some 2.4 GHz video links, which still seem to exist, then you make sure that if 1 or 2 of these channels are knocked out, still on the 3rd channel, you can see this announcement packets. So essentially, this IoT devices essentially hop through the 3 channels. You will later see that it's really as simple as I say. Transmit this advertisement channels, and then basically most of the intelligence happens on the other end. And yeah, then the remaining 37 channels are data channels. And again, basically like for example, if you compare it to traditional Bluetooth, where you have the super scary and super fast hopping with randomized hopping patterns and similar measures. For example, if you don't have the key, you don't know the hopping pattern and stuff like that. But again, like, which from a security perspective is very exciting, the hopping pattern on BLE turns out to be super predictable. You don't have to know any keys or anything. So a lot of interesting attacks are possible against BLE devices. And the protocol is truly, truly, truly simple. So you have a packet that starts basically with 1 byte, which is a preamble, and that byte is either 55 or AA, depending on the address that follows right after that, which is just 4 bytes. And when you send out something to the advertisement channel, then you send it out with this magic address, right? So that already specifies your target. And then you can have 2 to 29 bytes of data. And you can already see there is already like restrictions about the application. You probably won't want to do like video streaming or something, because it's not really fun to pack stuff into 29 byte PDUs. There are some exceptions, so like you can actually renegotiate this transfer unit if a device supports larger units, but essentially it doesn't get much better than that. So the simple answer is don't. Yeah, but it's super exciting for sensors, and especially like sensors which would where you would expect battery lifetimes of years. And in my experience, basically, when you do this IoT stuff, what people often forget is the cost of installing the system or like wiring up a system. So many applications are killed by the need of wiring the thing up or exchanging batteries. So when you can design a system which is super power efficient, so you have like 1 battery and the battery covers the lifetime of the device, which usually would be like whatever, 4 to 8 years, you would expect at least, then suddenly it enables applications which weren't possible before. And that's, I think, the actual interesting part of this Bluetooth Low Energy technology, that you have basic technology where you suddenly can do stuff cost efficiently and just with batteries that are not even rechargeable, because, for example, recharging circuit and the contacts and making that, for example, waterproof, or like inserting that into walls or concrete, it's not really possible with existing Bluetooth standards. So that's the interesting part. So like small data, irregularly sent, like every second or tens of seconds, and usually just low bandwidth stuff and notifications. And when you basically actually something happens, you can still create like a slightly higher power connection to the device and fetch more information about an event. But basically, average data rate and bandwidth low, Bluetooth Low Energy, perfect. That's the simple story. So yeah, this is how basically 2.4 gigahertz would look like. So we have this 3 orange advertisement channels. You could basically hop around Wi-Fi, but the picture, I think, is misleading a bit. Actually, you also need to see the temporal aspect. So basically these Wi-Fi channels are like 35 megahertz or something wide, whereas these Bluetooth channels are just basically like 2 megahertz wide. So under normal circumstances, you never have like constant strobe on a channel with Wi-Fi, right? So you have like a temporal aspect. So the reason for collisions, I think that it's highly, highly improbable, right? And then basically the difference in modulation width also makes essentially the game much easier for both parties. So there is very little interference between Bluetooth and Wi-Fi in my experience. So yeah, so by the way, the installation we did with our tracking is basically probably on one of the most densest Wi-Fi networks in the world, on this Chaos Communication Congress, where you have like usually like 3,000, or back then you had like 3,000 plus visitors, each at least like 2 Wi-Fi devices, and they really have kick-ass access points which support aggregated bandwidth of several gigabits in a room. So like you won't get more bandwidth in a single room than there, and we never had even like the impression that there is even a remote problem with that. So, but because we don't insist on a protocol that requires both-way communication. So if you lose a packet, it doesn't matter because the next packet you receive with a high probability. And in other protocols where you have both-way communication, you quickly end up in a loop where, so, oh, I didn't receive the packet, please send it again. You create more traffic, everybody creates more traffic, and the whole system grinds to a halt, right? So keep that in mind when designing such systems that should scale. And here is a simple example about a Bluetooth packet, the well-known iBeacon from Apple. So again, you see the preamble, the target address, which is the advertisement channel, this protocol data unit, which is as large as possible, according to standard up to the 39 bytes, and the CSC. And the data itself is dirt simple. So the first 2 bytes tell you essentially if the beacon allows to be connected back. If, for example, the beacon additionally supports proper Bluetooth, so it's a very simple thing. So it's part of the Bluetooth standard. It's freely downloadable, so you can simply have a look at that. It doesn't cost any money. And you have a target address. A source address, basically to indicate, oh yeah, basically I'm the guy that sending out this advertisement packet. And you can already see basically the security implication. So if basically you have full control of this packet, you can pretend to be any address. We'll come to that later. And then basically, at the end of the day, you just have exactly 31 bytes left, which again, basically is further limited. So in the Bluetooth standard, you have basically further stuff prefix, which is FF something, which indicates, oh, that's something that is not specified in the Bluetooth standard. Then part of that is a vendor ID, said, oh, it's Apple's special stuff that is not specified in Bluetooth. And then Apple actually just has this 16 plus 6, 22 bytes left. So that's actually stuff if you're really good. And that chip is already sailed because these 2-byte vendor IDs are already gone. Basically, they were limited. So if you start a new company, you use a much larger ID now, and you wouldn't be able to create an iBeacon now with a new company, which is a bit weird. And essentially the iBeacon is just a globally unique identifier, which you just invent. And you have 4 bytes as a guy that uses iBeacon to use. So you basically, as the bottom of the food chain, only has 4 bytes left, and you have to maintain this unique identifier. And that's the most interesting part. You indicate basically your antenna strength. It's a combination of transmit power and antenna strength. And by having a calibrated transmit power, you can roughly estimate the distance to such a beacon. Because you know with what power you picked it up, you know the transmit power including the antenna, and then you can do the math to figure out the rough distance. But beware, it's highly dependent on the environment. So if you have even like curtains in between or something, or like a body in between, then if you have a body in between, then rule of thumb, your distance will look half as close as before. Half as far, because like you have less signal, so you will look twice as far away from the reader as without someone in between. So if you would be in a conference and you don't set up your readers high enough, and you have on average a person between you and the reader, you can imagine that the triangulation wouldn't end up in a good place, right? So second, here. Okay, so what we created is basically, I skipped a slide. Yeah. Okay, so what we created is basically this OpenBeacon tag, so you can circulate that. Currently it's transmitting. So if you have an app that detects Bluetooth energy devices, feel free to run that now. It will show something surprising. And essentially what we did is like a compromise of make it cheap and make it exciting. So what we added is, for example, 3D accelerometer. So the idea is you can basically increase the battery lifetime with that. So for example, if you put a thing on a desk, the thing can sense that and, for example, stop wasting battery power. But when you put it on, you wear it, then it would actually use that battery, which would be an interesting case for the tracking. So our stuff is normally, we don't sell that currently because we don't have the resources to deal with people. Usually our stuff is used by academia for detecting social interaction in hospitals and doing basically infectious studies. So there were several large installations also open to the public, like in Dublin, a science gallery. They used OpenBeacon tags to, for example, simulate the spread of viruses between these beacons. So basically the beacons were transmitting a virus and another beacon would pick that up, the blinking pattern would change, and you had to go to a disinfection station, and you had this like nice, playful approach to infections. But it's used in proper scientific studies. So for example, it's used in hospitals to detect like hand washing patterns or how, for example, hospital staff interacts with, for example, guests or with patients. And then you have a data set where you can run infection models against, because infection models so far were depending on assumptions, which turn out not to be accurate. And so there is a sister project where basically we provide the hardware, which is called sociopatterns.org. So if you're interested in basically this like academic studies using OpenBeacon, then go there. There's now like at least a set of like 30, 40 scientific papers that were using OpenBeacon tags in various environments. And as a result, we created this new, that was the reason actually to create a thing. We added an 8 megabyte flash, so you can actually store this contact patterns, and you essentially hand out these tags to people, so they can basically interact over a month's duration. And after a month, you collect these tags, and then you have the contact pattern over a month without, for example, in a large hospital environment, it was too much effort to spread out these readers. And with this offline logging, you can see it would be much easier. And the interesting thing is that accelerometer is very, very low power. So it can do things like, for example, also detecting movement patterns. And later in a post-processing phase, you could infer what the person was doing at a given time. Person was sitting or walking or cycling and so on. So you can correlate basically the things you see with the movement patterns. And so that's also one of the latest members of our stuff. So we created a new reader, which is BeagleBone Black based, which has basically two wireless interfaces and a real-time clock, which is essentially also the idea is to use it in this hospital environments to basically capture data if you, for example, if you want like real-time communication patterns between people. Last but not least, that's basically a debug adapter, which has a serial port where you can simply plug in one of these tags and have a serial port, and it doesn't suck too much if you have to program 1,000 of these. So you just like snap the thing in, and it connects with the spring-loaded Pogo pins. Okay, so let's go to the interesting part. So toolchain installation. So currently, because I'm lazy, I'm developing primarily on Linux and secondary on OS X, OS 10. I personally use Fedora, but I also successfully using that under Ubuntu. It might work with Windows, but don't expect me helping you with that. So conceptually, it should be very easy. ARM thankfully maintains a GCC ARM toolchain, a Launchpad, which is super updated. So just download that. They have it for Windows, OS 10, and Linux. So just use that to be on a safe side and always take the latest version and update it from time to time. There is basically Nordic Semiconductor from the company that built basically the wireless chip on these things. There is a development kit, which I misuse as a debugger, because that's the cheapest way to buy a pretty good debugger, to buy one of these dev kits. The dev kits cost around £50, which is way, way less expensive than a professional JTAG debugger. So yeah, get one of these. The things are backed with links. If you go to openbeacon.org, you should be able to download the slides and use all the links. And then download this JLink software, which is basically a pretty rock-solid debug software for ARM CPUs. I'm pretty happy with that, which supports this NR51 development kit. And then basically go to openbeacon.org to get the sources. So it sounds like a lot, but it's way easier in my opinion. But here I am and doing that stuff than normal like embedded development. So it's pretty straightforward. Like this JLink software comes with a proper installer even for Linux, so you don't have to be a wizard to install that stuff. And same with the debugger is self-explanatory. And I will create some tutorial videos about that once I find the time. So I want to, I think the three most important example codes you will find on basically OpenBeacon website is basically this iBeacon example. So it simply does this announcement packet stick, which I showed you just before. It has a canned packet which contains a URL and transmits that into the wild. And if you install the corresponding app on your iOS or Android device, then you get notification, oh, I'm close to the device, here's a URL. And I'm very excited about that, because one of the problems with Internet of Things is that usually the user interfaces suck of this device. You have some embedded web servers and it really is a nightmare to use. But if you basically think a bit ahead and think about, actually the device doesn't need to serve the user interface. The device only needs to point you to the place where the user interface runs. You don't need to squeeze the user interface through like this tens or hundreds of kilobits of Bluetooth low energy bandwidth. Actually, you run the user interface basically on a cloud service or on a local machine. And then basically this physical web token comes in that announces just basically the UI, and you basically quickly start basically a full-blown user interface. You can interact sanely with a UI, and then you just transmit the bare minimum data to the device. So you have a snappy user interface. So that's, I think, the physical web thing. Like, if it will be called physical web in a few years, I don't care. But the concept that a device announces basically a cloud endpoint locally, that makes total sense to me. Because also, like, if you have like 5 devices or 10 devices, 20 devices, how do you know which one is which? I want to walk up to the thing and see the user interface, right? And that's both possible with iBeacon, and that's both possible with the physical web token. And basically the third aspect is this mischief tag, which I want to use to essentially rub it into Apple's and other companies' faces that they suck at security and privacy. And the point is, if you rub it into their nose early, then they might change something about that. So yeah, I'm starting just with that. I will talk about that later. Okay, so this is basically how you would, for example, develop for this physical web token. So there was just a git clone. You basically get the source code. That's basically the main loop. That's all. So you define basically this advertisement packet as it is. So that's basically the payload for the advert. Oh, you don't see the mouse pointer. Damn it. Yeah. So that's basically the payload and the URL. So Google found a nice way how to compress the URL. So essentially you don't have to spell out the HTTP. You instead have a byte that says, oh, it's HTTPS or HTTP, which is pretty sweet. So you can pack more data into basically these 20-something bytes of advertisement payloads that are remaining. And everything else is taken care of on the other side. So for example, Google created a reference implementation for registry server that can resolve basically these requests in a privacy enabled way, and also is able to cache metadata about basically your target URL. So basically you don't have to visit a website to get a rough idea what the website is about. So when you basically install that software, so it's basically once you installed basically the toolchain as described, it's just a make clean flash. So basically the makefile takes care of that, and the debugger to flash the firmware into the device. And when you click basically on this notification, it's actually not a notification, you just get this a symbol. And you click basically on that and then on the tag, then you will get information about that website, and then you can decide if you want to enter the website or not. So the security example I created essentially just iterates the stuff we created. It's essentially as close as you can get to the hardware as possible. So you really literally talk to the hardware to set up basically the frequency, set up basically the whitening, which is frequency dependent and channel dependent. You configure basically the Bluetooth address, and you initialize the mechanism that calculates the checksum. And once you did that, you, for example, can do things like configuring the hardware to intelligently switch between different states. It's very nicely explained in the datasheet of that CPU. So basically, you don't need like to run interrupts or software to do like basic tasks. For example, after you can be very, very power efficient by, for example, hardwiring. Okay, the crystal clock is now established. After it is established, run, for example, the transmit routine. After the transmit routine is on, disable automatically the radio and go to sleep. And you don't have to involve software in that. So on a normal circumstance, you would have like 3-4 interrupts, which would be very power hungry. But if you wire up basically these events in hardware, and you can even go as far as wiring that up to an encryption or decryption algorithm, then you just get actually the decrypted data, and it's a result of a chain of hardware events that were completely handled by the hardware without waking up the main CPU at all. Just pretty sweet. Clock, I have to rush now because I'm running out of time. But you have basically a real-time clock. So basically that thing is just configured to a second's time. And what it does, it has a large database of word snippets, and it just makes up tag device names, and it simulates basically, because I have no limitation in my own stack, 23 tags concurrently. So basically this one tag is now circulating that transmits currently 23 tags with totally ridiculous names. I'm not sure you can read that. You can't. But you can later have a look at my iPad, or if you have an iPhone or Android phone, you can scan for BLE devices your own on yourself. So here, you can. So these are the devices you would see appearing, and like it's an unsuspicious example, but it's already like would prevent you from using a valid BLE service. Imagine basically you are in a store, and you have basically this tag which is just glued with a piece of blue tag on the table, and it would basically spam the air with made-up names. Under no circumstances it would be able to use existing Bluetooth locationing service. Go a step further. Have this tag that records, for example, iBeacon transmissions. You take these transmissions, randomly play them back with random signal strength. There is no way your locationing works. You basically completely destroy the locationing in a whole building by one thing that runs from a coin cell for half a year, right? And that's just the start. So like you can do really, really nasty things with that, and it's not difficult, and people don't care, right? So Apple doesn't care. There's no authentication. You can just take the stuff on the air, retransmit it, random thing. Imagine you have a tag, you carry it with you, and it picks up iBeacon transmissions while you walk through a store and plays them back somewhere else. The locationing totally blows up. In London, I heard that's 2 days ago, they start deploying iBeacon locationing in the tube for blind people. If you don't like blind people, you have basically your tag that picks up the iBeacon transmissions and plays them back with 10 minutes delay. Good luck if you are blind. But the point is like they don't care, right? So if you really want to do nasty stuff, you essentially start from zero, and you will have a fun time. Questions? So there are some advanced examples about how the thing is used, like on conferences, how you connect that to databases, how you do real-time locationing. There is, for example, in Redis and the MongoDB example where you can use basically MongoDB has, I think, 2D database queries. You can say, show me the people that are in this arbitrary shape and stuff like that. And you can see the real-time contact networks on like conferences, hospitals, whatnot. So that you find all on that web page.